All right, so before we get into the demo, I just want to kind of go over the high-level architecture of this real quick, just to keep in mind as we go through this. So the core of GoLlama really is the GoLlama Hub, that's kind of the API that we've been talking about, the inference API. That's kind of the meat of it. However, you can think of GoLlama more as a platform because there's actually several other components that go outside of this API. So you do have the API here, which is doing the parallel task handling. However, you also have the GoLlama workers. So, again, think about you've got these volunteer users out there who they've signed up their computer to run instance. Let's say, somebody has a nice big gaming graphics card on their computer and they want to, in their off hours, they want to share this to the broader internet community. So you've got these, you have basically a GoLlama worker app, which is a thin wrapper around Llama CPP, which basically just talks to the GoLlama hub, gets that connection and routes requests through to the underlying Llama CPP backend. So that's basically all the worker is. And then you have a third component, which is actually the user themselves. And we are working on a user interface so that people can communicate through that and, sign in and things like that. But, that's kind of still a work in progress. So we're just going to show that through HTTP requests for now. So yeah, again, you've got these three components. You've got the hub, which is the API, the workers, which are basically these Llama CPP instances off on different computers all around the world. And then you have the actual user, which might be on a very low-end computer that doesn't have access to, lots of compute, and they also don't want to pay someone like OpenAI to use these machine learning models that are so helpful to everybody. So let's dig in straight to the repository, and I'll kind of show that architecture here just to keep that in mind as we go through this. You can see I've got several different terminals. We're going to do everything through localhost just to kind of simulate that concurrent nature, but we don't want to mess with the complexities of actual networking and security and everything like that. So this just simplifies it and lets us focus on the core features. So everything is happening on my one machine. So this right here is the GoLlama API term. This is a terminal that I'm using for the GoLlama API. So I can just hit go run, command GoLlama main go, and go run is basically just the shortcut command that lets you build and run without actually having to compile. So it's just a kind of a nice shortcut, but you would want to build for production. So we can see a few endpoints that are made available. This is just a little bit of preview just to kind of let you know what is made available. And so we can see GoLlama is working. Now, this worker 1, 2, and 3, these are kind of those GoLlama workers or GoLlama workers that I was talking about before. So these would be the people who volunteered their graphics cards or CPUs or whatever they have up for inference for other users as, like a volunteer system. So again, these are local on the machine. So we have basically this worker main go. This is a separate app that someone could download separately. And here we're exposing it on port 9001, and we're connecting to Llama CPP at port 8080. So that's just a flag to denote that. So when we hit that, we can see auto connect successful, and we also got connecting to Llama CPP on port 8080. This is that's the back end of where the actual number crunching is happening. So here in the terminal, you can see we have port 8080 exposed, and this is a Llama server running. So we can see we just got to get health because that's what the worker does when it first instantiates. When it first builds and spins up, it tries to shoot a quick, simple health message to Llama CPP to ensure everything is working before it connects to GoLlama. So that is that, and then we'll spin up a couple extra workers. Before we spin up a couple extra workers, I'm just going to shoot out a couple test messages. We're just using, instead of a user interface, we're just using Insomnia to send HTTP requests. So I'll go to the GoLlama Health, and you can see if I hit this, we have currently 1 worker available. And when I go to GoLlama Chat, I just have a message that says provide a function to calculate Fibonacci of in Python. And when we send a message, you can see executed task at endpoint. That was worker 1 running this task. If we go back to GoLlama, we see a couple things. We see added worker, so we know we have worker 9001 connected, and then we got the received message. Processor 5 picked up the job, and it was sent to worker 9001. So processor 5 is kind of the parallels feature for Go, which we're using to allow concurrency. So we spin up lots of concurrent processors, and so it's kind of indeterminate which one is picked up, but that's just something to note. We'll go into that a little more in a bit. But you can see we completed that task in 1.89 seconds. So I'm just going to go ahead and spin up a couple more workers here. So I've got worker 2 here at a different port, and worker 3 at yet another couple ports, because I'm running several instances of Llama CPP here on my machine. Again, only one humble process CPU, but you know what, it's doing great, so we're going to keep going. And now we have 3 workers assigned, as we can see in the GoLlama terminal. We can see those 3 workers signed up. So I'm going to fire off just like maybe 5 or 6 of these chat requests. They take a bit to run, again, because I only have so much horsepower in this laptop here. But we're going to run 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see they're kind of got queued up, and now they're shooting off. So the queue depth is 0 because they've all been sent to processors, because we do have 10 processors that can handle that. So while it was running through doing multiple jobs, they were immediately picked up by those parallel processors. So you can imagine a scenario where there are actually 10 workers. You could send off 10 jobs, complete all of them at once through the 10 processors, and send them all back at once without getting tripped up on any of them. So you can see that completed, and several of these, all 3 of these Llama CPP instances were firing. So if we go back to here, we can actually see this GoLlama stats endpoint. So I want to just take a minute to go through this. So when I hit send, what we're getting is basically a list of all the workers that are signed up and some lifetime stats associated with them. So you can see this worker's been up for 3 minutes and 48 seconds. That was the first one we signed up, 9001. Then we've got 1 minute 38, 1 minute. So, you know, we have some, maybe some lifetime metrics that you might think of. And we also have, importantly, this score. And so the way we're calculating a score is jobs completed times uptime seconds, you know, with a factor. So the idea with score is that we want to use it for a couple things. One, we want to use it for determining which are the best workers to use in the pool when a processor selects a worker. And then 2, we also would love to create a leaderboard where different users who volunteer their graphics cards or their compute can go in there and see how awesome of a job they're doing, and maybe give them, you know, some sort of bragging rights, community flair, some sort of, you know, something to kind of appreciate that they've done so much work for volunteering their compute hours. So that's kind of a simple calculation for score. We've thought of lots of others which have related to tokens per second, model types, you know, different categories for different kinds of models that you use. But for now, we're keeping it, you know, pretty simple just to show the concept. But that would be the main idea of the score, is one selective worker, choosing which worker based on your, you know, kind of weighting towards a higher score, because we want to, you know, if someone has completed lots of jobs, that means they get jobs done quickly. And if they've been up for a long time, that means they're more reliable, right? We don't want to send a job off necessarily to a worker who's only been up for 5 minutes. We'd rather send one up who's been alive for 5 hours, because they're more likely to be available for 5.5 hours if they've already been available for 5 hours. So just, the idea would be to kind of improve the overall health of the system by keeping a track of who's doing the best job of running these jobs. So that is GoLlama stats. Now I just want to go into the meat of the program a little bit and show a couple of the different data structures that we're using to make this happen. So kind of, we have our handler folder here, and these are basically different endpoints, right? We've got, I actually forgot to go through a couple of the other ones, so I'll do that real quick. We have chat, of course, which I did. Then we also have sentiment. So this one says, I love it when you do format JSON strings correctly. And that's a positive sentiment. If we switch to I hate it when you do not format JSON strings correctly, we get a negative sentiment. So these are just kind of different endpoints that might be useful to a user if they want to classify the sentiment of something or otherwise. And then we also have summarize. Here is the first few lines from Cinderella. And we have a pretty small model, but it does its best. Cinderella's mother died, her father remarried, her sisters were harsh. So, kind of the opening act of the Cinderella story. So that's kind of what the summarize does. It doesn't actually respond to you. Instead, it's being told within our system, hey, can you please summarize this? Just as a quick tool to help out the user's workflow. So going back to what I was discussing before. So we have these different endpoints under the handler folder. We've got chat, we've got sentiment, stats, summarize, translate, and health and stats. So, these are kind of just the different features that you have exposed via HTTP to the GoLlama server. The underlying data structure is being handled mostly by server and pool. Pool is kind of the meat of it, so I'll go into pool right now. And so the way pool works is it starts with this start method. If we can go, let's see, start, match case. Right here. Okay, so here's the start method. And so this is initialized when GoLlama runs up. And you can see it's basically just running a for loop and saying go pool.jobProcessor. So this is a method for the pool object, which you can think of pool almost kind of like a bag. This is basically realizing that these workers are fundamentally a little bit unreliable. These are volunteers who they could have their power go out. They could just decide they don't want to submit time anymore. Their computer, they could spill their drink on their computer, whatever. There's lots of ways. This isn't a dedicated CPU instance. These are somewhat unreliable workers. So we want to maintain kind of a large pool of these workers that can come and go freely and should not affect the health of the overall system. So that's kind of the goal of the pool object. But you can see here, the Go processor runs these different coroutines, and the job processor is kind of the meat of what runs all these different endpoints. So if we hit, we can see concurrent workers, and so I think this is a variable we've set in our environment, our .env, which I think we have it defined somewhere between 10 and 50. So that's kind of the idea for job processor. So if we go into the job processor, going back to that concept of the concurrency, these are all running indeterminately. So again, these processor numbers is what you're seeing here, where you have 1, 4, 2, etc. They just pick up jobs as soon as they're available, and it doesn't matter who picks up the job, just that a job was successfully picked up. However, we do have to maintain coherency in the underlying data structure while we're doing that. So the way we do that is through basically the mutex object, which is kind of like a thread lock. It's a little bit different in Go, but it's basically a thread lock. So if we go into, you can see that if we did a successful job, then we want to update the stats and send back out the result to this reply channel. So if we go into update worker stats, you can see the first two lines here are pmu lock and pmu unlock. P is just the pool object that we've been referring to. mu is this mutex object that is that is instantiated in the pool, and then lock and unlock. And so all that's happening here is as soon as we start the job, we lock it to make sure no one else can run this method while this processor is in the method. And then defer just says as soon as the method ends, run this function. So defer is just kind of a useful way to connect the start and the end together. So you don't have to remember to write this at the end of the function. It kind of just keeps it there, makes it a little bit more readable as to what is happening here. So that's kind of the idea there, because we are actually printing. We see we're updating, we have stats, and we're incrementing. And so you can imagine a race condition where if two processor tried to hit this at the same time, you could get IO read errors. So that's just kind of the idea with mu lock and unlock. And the overall pooling object is kind of exists so that we can handle, revolving door number of workers. So that's kind of the idea there. I'd love to go into more detail about future work and what we'd love to do, but I think we're about out of time, so I will wrap it there. Thank you.